So we've been talking about where light comes from, but there's actually more than one kind of light. When we've said Roy G. Biv, but Mr. Dimitrievich, there's more than just Roy G. Biv.
Yeah, Roy G. Biv is all we can see. And there's actually something called the electromagnetic radiation spectrum, EMR for short, for us nerds that like to say that.
EMR.
But there's a ton of different ways. In fact, if we were to stop right now and see all the waves that are hitting into us, it'd be crazy.
Yeah, it'd be crazy.
There's trillions and trillions of waves. Like right now, we're sitting there, radio waves are hitting us, TV waves. We hope not X-rays, but any type of wave could actually be hitting us.
And in fact, my phone, and your phone too, works on something called microwave. So microwave radiation is hitting this, and when a certain pulse comes in, it says, I have a phone call. So when we talk about the other types of light, right, then we have the electromagnetic spectrum. And you can see on one end we have this funny looking Y thing, that's gamma rays, and then we have X-rays, ultraviolet, visible, let's talk about visible a second, infrared, microwave, and radio waves. And now you've heard of all these things, microwaves, you've heard of probably X-rays, you've had an X-ray in your life, but notice this narrow band right here in the middle, that is the visible light. We can only see just a narrow band. Our eyes can only detect just a little bit of the actual light that's actually in this room, or EMR, as you would like to say.
We call them waves, yeah.
Yeah, so, and it's crazy. Now, what makes them? What's like the big property? We say electromagnetic radiation. They have this strange, like, wavy thing. What's that?
So it's a form of energy. So energy hits us all the time, but energy travels as a wave. So all of these waves, what they have in common is they're all moving like a wave.
So let's take a look and talk about the properties of waves. So I think you've got a couple of waves you want to draw.
Yeah, so I'm going to just draw visible light because I'm not going to be able to draw accurately an X-ray. But let's say we take red light, which is a longer wavelength. It's going to go something like this.
So it's a wave, right? Like a water wave at Galveston Island, right? But what about a blue wave?
A blue wave, again, it's going to be similar, except you're going to have a lot more waves in the same time, in the same area.
So now we can measure some things about these waves. What could we measure about the waves?
Well, the first thing we talk about is wavelength. And so anytime you take any point where it repeats itself, we call that one wavelength. So there's actually a symbol, we call it, that's the lambda, Greek lambda symbol, and that means one wavelength. Now if you take a look here.
So it could be like a meter long, or it could be a nanometer long.
Or in fact, he sold it short. We have radio waves that travel, that literally are miles long, and that's why you can sit out there with if you're that level of nerd, as we sometimes are, you can actually sit up with a ham radio and you can get these really long waves that travel from Russia and such.
They're miles and miles and miles in their wavelength. And so notice the difference here. This is the lambda, the wavelength from the top of one wave to the top of another. We actually call this the crest of the wave, the top. The bottom is the trough of a wave. And you know that probably from,
the crest
surfboarding at Galveston Island, right?
Now, one of the things that's the only difference between red light and blue light is that their wavelength is different.
But what's the same? There's something else that's kind of the same.
They all travel at the same speed.
They travel at the same speed, so they all are moving with a velocity v. And how fast do they move?
It's 3.0 times 10 to the 8 meters per second.
Now, that sounds like a lot.
Yeah, this number right here times 10 to the 8 meters per second.
Put that in some terms that will help me understand.
Okay, so let's do this. You're pretty fast. I see you were exercising. I clearly have lost a step since my college days. So let's say that we were going to have a competition, and you, Mr. Bergman, we're going to have you run as fast as you could, as far as you could in 1 second.
Okay, sure.
We're gonna use our imagination. We're not gonna actually have him run, but imagine, if you would, him running. I have a stopwatch, and I'm gonna go. All right, go as fast as you can in 1 second.
1 second. That's
Boom.
fast.
In our imagination,
do I get like a head start?
You can start. I'll tell you what. I'll even give you 2 seconds to run. But how far do you think you could run in 2 seconds? Like in this classroom, in our classroom right now. Picture, if you would,
2/3 of the way across.
2/3 of the way across.
Maybe 8 meters.
8 meters. We're just making up.
No, I can't make 8 meters. 4 meters.
So 4, 8. I'll tell you what. Let's say you could run half a football field in a second. Which is crazy.
That'd be
fast.
like Flash.
He'd be winning Olympics right with that.
Yeah.
If you were running against light, and I said, all right, Mr. Bergman, go, and you ran half the distance
football
of the
field. Man.
And I compared you to light, and I said, light, you do the same thing. Light would travel 7 times around the Earth in that same second.
Oh, that's fast.
So you got smoked, son.
Big time.
Yeah, and that's
light travels crazy.
I had some students in one of my previous classes that had one with a stopwatch, another with the light switch, and they were like, click, click. And they're like, ooh, we cannot measure light that quickly because it's infinitely faster.
So when you turn on the light, it feels instantaneous, but the reality is it does take time to travel. Now this happens actually at the astronomical scale. So if I want to send a radio signal to Mars, Mars is actually about 8 light minutes away. So if I send a radio signal, and radio waves, electromagnetic radiation, travels at the same speed, it will take 8 minutes to get there. So if I wanted to call you, you got sent to the first trip to Mars, I'd call you and I'd say, hey, Mr. Dimitrowicz. 8 minutes later, you hear it, and then you respond and say, hey, Mr. Bergman, and then another 8 minutes, like 16 minutes.
I mean, certainly we might dispense with the formalities of, hey, mister, when you have that long of a time between.
Yeah, you just have to text message or something.
It is pretty crazy the amount of time it would take. Now, I will say this, and this is kind of tricky. It's kind of like rubbing your head and your, what's that, the thumb? Try. Because all waves travel at the exact same velocity. So that means this. If I were to take a point on this wave and a point on this wave, they would reach the end at the exact same time.
Right.
Now this travels more like this travels more like this. Now, can you give a way to explain that a little bit better?
So think about it this way. If these waves are moving exactly the same speed, the wave front is going to hit me. So I'm standing at the beach, right? And I have long wavelengths, the red one's hitting me. They're going to hit me like that. But the blue waves, if they're closer together, again, they're still moving at exactly the same speed, but because the wave fronts are hitting me, they're going to hit me, if you will, faster. The wave fronts, or more frequently, is probably the better way to say it. But what do you think's gonna, which is going to hurt me more?
Well, clearly this is going to hurt you.
Yeah. So the shorter the wavelength, the more energy it is.
In fact, you could even look at this. If I were to do 2 waves just with my hand, so this is wave number 1, right? And this is wave number 2. You can tell just by that, and by the way, that's not an exaggeration of the comparison between a red light and, let's say, an X-ray. I couldn't even get the up and down motion quickly enough, but clearly when you have a shorter wave, you're going to have a higher energy. Now, our pre-AP kids, we're actually going to do some calculations on this, but as far as you need to know is the longer your wave,
the less the energy.
And
if you have short ones, like X-rays are really crazy short. Let me tell you a real story. My grandfather got his medical license in 1920 something. And when he was they discovered this cool thing called a fluoroscope. And so let's say I'm Dr. Casebolt, his name is, and Mr. Dimitrowicz, you broke your arm. He would come and he would put it on the table and he would put a fluoroscope there and he would set the bones of his patients. See, in the early 20s, they didn't know that X-rays weren't very good for you. And so my grandfather, sad story, he died of cancer, lung cancer, not because he ever smoked a cigarette, because he never did. It's because he got radiation poisoning in his arms because he'd been using these sort of upside down X-ray machines for so many years before they said, oops, not such a good idea. So, and again, it's just this light, but it's so close together, if you will, such a small wavelength that energy can damage human tissue.
Well, even go one step farther. If you take a look at gamma rays, let's take a look here.
Gamma rays even worse.
So gamma, if any of you guys have had family members who have ever had cancer or whatnot, gamma rays, look at how small they are in the scale here. They're incredibly tiny.
And then very, very high energy.
Which means they have incredibly high energy, which means that if they're trying to damage something, when it hits into things, it's kind of like a little grenade you're throwing in. So if you have a cancer radiation treatment, what they're doing is they're bombarding your cancer area. The problem with that is that
it also hurts the other cells.
It's indiscriminate. So they try and very pinpoint in a very small, but it ends up hitting more. But we need to be aware that all of these, like the only difference between gamma ray and X-ray and light we see and the TV we watch
is the length of the wave.
Is the length of the wave, which has all kinds of other repercussions.
And another side note is we look again at our table here, ultraviolet. You've heard about how bad ultraviolet radiation for getting
Skin
sunburns and eventually skin cancer, but notice ultraviolet is on the other side of purple light, indigo violet. Ultraviolet makes sense if you think about it. It means it's shorter and we can't see it. And one last thing I think is super crazy cool is that we can only see from, is it 400 to 700 nanometers?
Correct.
So our eyeballs are detectors for 400 to 700 nanometers. A nanometer is a billionth of a meter. But there are animals who can see in the ultraviolet spectrum and some who can see in the infrared spectrum. And the question I would ask is, what color do they see? See, we can't, it's like blurper. I don't know, so make up a name. Blurper. It's the new color.
Blurper?
Yeah, I don't know. Call it what you want. Roy G. Blib Blurper. It's some color that like some insects can see in the ultraviolet, and some animals can see in the infrared. Some like I don't know, like snakes and stuff like that.
So in closing this up here, we're going to dig into this a little bit more deeply, but it is crazy cool how it is we see things. And a lot of things have to do with waves, and we're going to draw that correlation between waves and electrons and other things.
Because we're really talking about what's the atom like, but you have to understand light to understand the atom.
See you next time.